Hey. Enough of that, right? All right. Section 2.2, contextualizing linear functions. Okay. First, you were supposed to read and highlight. Let's look at that. Let's look at some of the things that you highlighted. Before we even begin that, what does contextualize mean? Big word, lots of syllables. What does contextualize mean? Ashlyn?
Kind of fit into like talking or
putting it into a real context or real situation. Okay, we're looking at the real world situation. Now, as we start talking about 2.2, we're going to talk about all the parts of linear functions, remind ourselves of what linear functions are, what their parts are. And once we know that, which we already do, you'll find, then contextualizing it becomes a lot easier to do. Okay, figuring out what the context is. This is one of my favorite parts because this is the real part. This is where math isn't just a bunch of numbers, where they have real application, real logic. I tell you that all the time. Math isn't just numbers and calculations. It's logic. It's problem solving. And this is where we spend our time focusing on that part. I hope that when you were reading and highlighting, you started by right away highlighting these first several lines. A function is a graph. A function whose graph is a straight line is linear. A function whose rate of change is constant is linear. A function whose equation in the form y equals mx plus b, where m is the slope and b represents the y-intercept. I hope that you started by highlighting that. How many people highlighted that? Excellent. If you didn't, please do. Okay, there's something important to me, though, that's missing in that. We talked about what is a linear equation or a linear function. So what's missing from those definitions? Anybody? Ashlyn? Very good. Has to be a linear function is a function to the first degree. I'm going to highlight that too. Hope that, all right, it didn't do it. Yes. So many times when I write something in pen and then I highlight it, it smears the ink. It didn't do it to you. Anybody? Thank you. It's digital, duh. All right, so a function to the first degree is also linear. And then you went on to read about these independent and dependent variables. What are the independent variables? What are the independent variables? Luke? No, it's not B. Look, I got it highlighted right here. Independent variable is the input. So independent variable is just another name for input. So what's dependent variable? Output. It's the output. Okay. Now I don't care what you highlighted. I'm not saying what I highlighted is right and what you highlighted is wrong. I'm not saying at all. What you highlighted is what you need to highlight. What you highlight may not be the same thing that he highlights, and that's okay. Because what do you highlight? What makes sense to you? What makes sense to you? Somebody else may need something different to make sense of it, okay? So I'm never looking at your highlighting to say, oh, this is right and that's wrong. Never am I looking. It's just what makes sense to you, okay? Just trying to help you learn to be a good student. For me, at my level where I'm at, that's probably all I would highlight in those sections. But back in the day, I probably would have highlighted some of those full paragraphs because it was an example that made sense to me. Are you with me? Moving on to the next one. I'm on the page 70? And I specifically want to look at this top line. I would like you to highlight it if you have it, but it says in the standard equation form of a linear function y equals mx plus b. Now I want you to highlight because I want to talk about that. If you need to do a different color, please do, whatever. And then I also want you to cross out the word standard equation and write slope-intercept. Let me reread it. In the slope-intercept form of a linear equation, y equals mx plus b. Isn't that what we're calling it right now? Okay, and I want to kind of take a time out, and I want to explain why I just had you do that. Okay? So let me call my time out, and let's go over here. Don't write yet. Don't write. I'm going to have you write all this down in just a second. Okay? See, at some point, we're going to start talking about polynomials. Okay? Polynomials have many terms. This has 1, 2, 3, 4, 5 terms. Okay? That's a polynomial. And when we start talking about polynomials, we'll say, hey, we want to put those in standard form. But what does standard form mean then? That means get your terms lined up from high to low. What's from high to low? The exponents from high to low. That's what standard form means when we talk about polynomials. Okay? And in all in reality, this is a polynomial, 2x plus 1. It is. So it kind of is in standard form if we're thinking about polynomials. Are you with me? So I want you to take a second to write all this down, and I'm going to come back and explain this part. I'm going to give you 2 minutes to write all that down, and then I'll come back and explain.
I kind of messed my papers up whenever I hole punched you, so now I'm going this.
Sound like Luke?
This your brother here?
Adam?
This your brother?
No.
I think he is.
Yes. What to do?
Luke did the same thing.
Hey, Chuck.
Mr. Herman.
Yo,
I did.
What does it say next to standard form?
polynomial.
All in what? Normal? Yes. The heck is on?
Oh boy, are you lucky. Oh man, are you lucky. Put your packet back there.
Okay.
Slacker.
I just don't know how to hole punch.
You don't know how to use the hole punch.
Neither does Luke.
Hey, I got it on my second.
My time's not as bad as Luke's.
Second try to turn.
Come here.
Wait, I am. Yeah, they
You
hole
missed 2
punch.
feet.
Push it all the way in and down.
Okay.
Voila.
I got it on my second try, not my third try.
You just slide it in and down and push.
Thank you. I just don't know how to do it. Now I do though. Thank you.
Didn't even want to learn something that you did.
Huh?
Didn't even want to learn anything you did. All right, I know you're still right, but I'm going to go ahead and start. Standard form, as I mentioned, when we're talking about polynomials, is your terms lined up from high to low. But when we're talking about linear equations have their own standard form. And that standard form is ax plus by equals c, where a, b, and c must be integers. Okay, well, what's integers? I don't know what integers are, Coach Herman. Anybody know what integers are?
That's like 0, 1, 0, 2.
Yeah, they're all the positive and negative whole numbers. So basically, when it's in standard form, you'll never have any decimals or fractions. We like that. And then a must be positive. And that's all I'm going to tell you about that for now. It's not something we're going to be studying at this moment. We will in the future, and we'll come back to it. I just kind of wanted to use that as a chance to introduce standard form for you, and also just fix that one thing, just because I don't want to get you confused. There's enough confusing things in math, and we're going to call y equals mx plus b slope-intercept form. Is everybody okay with that? All right, so let's look at, let's go back. Everybody got that written down? No? Need another second?
Yeah.
What does STD stand for?
Standard. Also stands for sexually transmitted diseases, but that's in health classes, and this is not that. Okay. Here, that's shorthand for standard. Okay. You surely didn't think there was STDs in that math, right?
No,
Okay.
I didn't know what it stood for though.
Gotcha. We don't have those problems in the math world. All right. So also in your reading, you read about rate of change and slope. Okay, nothing was new there for you, correct? You may have highlighted a lot there. Y-intercept and the initial value, nothing was new for you there either, correct? It was all good for us. The only thing that really was new then for you was independent variable and dependent variable. I think I've only mentioned that in passing a couple times. So let's kind of pull that in a little bit as we talk about it. Independent variable is also the input, and the dependent variable is just another name for the output. Can you handle that? Okay. So let's look at our slope intercept form or talk about our linear functions just a little bit more. Again, what do we know about linear functions? How do we know something's a linear function? Straight line. Come on, baby. Come on, baby. Let's do the twist. All right, it has a straight line. What else? To the first degree. Okay. One more. Sorry. Yeah, that's just a function, not specific to a linear function. All functions have that. We're talking specifically about a linear function.
Constant rate of change.
Very good. Has a constant rate of change. Okay. Let's stay in red. Somebody tell me what's the name of the y. And don't say f of x. What's another name for y? The y, nope, not the y-intercept. It's not the slope, it's the output. It's the output. It's another name for m. The slope is the slope. What is the x? Input is our input. And the b. Let's go with y-intercept because slope and y-intercept go together, right? You agree with that? All right, so let's go to another color. Let's go purple here. And come on, purple. Another name for output. Range. Range. Okay. Another name for slope. Rate of change. Another name for input. Domain. Very good. Another name for the y-intercept. Initial value. We're good so far, yeah? I'll bet we can get one more name for each of them. Another name for output. Very, not independent. Dependent. Dependent. Variable. Another name for rate of change. What is slope? Rise over run. Another name for domain or input, the independent variable. And another name for the initial value or the y-intercept. Well, both classes have gotten this one. I expected to get some. Another name for initial value or y-intercept. Doesn't change.
Constant.
It's constant. Constant. Good. Good. Now see, we've learned all of that already. The only thing that's kind of new is the dependent and independent variable. Just kind of add those in. We know what all those things are. Those names. Okay, it's a lot of different names for the same thing. Right, JC? Right, Miss Herman? Right, Lizzie? JC Elizabeth Herman? All the same person, right? Just multiple names for it. This whole section of 2.2 about contextualizing is saying, figure it out in a context of a problem or a situation or an equation or a graph, what those four parts are. And if we can figure out what those four parts are, we can come up with an equation. And when we have an equation, obviously we know we can graph it and different things like that. But we're really looking for the context. So that's what I want to do. I want to do the first couple problems with you. Okay? That's really the only way there is to do this, is to identify the parts and then figure it out. Yes? Huh? Unless there's an emergency and you're willing to stay for detention. Okay? All right. So let's look at the first one. Basically, what we want to be able to do is identify all the parts and then think about what those parts mean in the context or in the situation. A 2.5 foot or 2.5 foot rocket's distance traveled in meters based on time in seconds is modeled by the following equation. What is the dependent variable? Skylar, how do you know?
Because we just did the thing about the slope-intercept form equation.
And
D is replacing Y, and Y we said was the dependent.
Okay, so he looked right here and found the D. How many people did that same thing? Did anybody do it differently? Okay. I want you to look at this one this way. Okay. What if that equation wasn't there? What if that equation wasn't there? Mia? Okay. Say that one more time.
You look at how long, you look at how the time affects the distance of the meters traveled.
Time affects distance. So which one is independent and which one is dependent?
Independent is P.
The T is independent because D is based on. You see that based? That means, hey, this is the one that depends on the other. So D is my dependent, and therefore T is my independent. See how we can find out that same information from the situation? Yes, Zach?
Isn't the rate of change 5 and the initial value 2?
It absolutely is. The rate of change is 5, my initial value 2. Now, in that particular case, there's no way I could know that from the sentence above, because it doesn't say, without the equation, it doesn't tell me a rate of change or an initial value, but it does tell me in the equation. And of course, this one's really easy to tell the equation in the line. It's just D equals 5T plus 2. So now, what's the contextual description of the rate of change? What does that 5 mean? Zach?
5 seconds. The distance traveled in 5 seconds.
The distance traveled in 5 seconds? How do you know it's 5 seconds?
Because it says T, which is time.
Okay, so T is my time.
Yeah.
That's my time. 5 is my rate of change. All right, now wait a minute. Stay with me. What is changing?
The time. No. The distance traveled.
The distance in time. So the distance in time. So my rate of change is 5 meters per second. That makes sense to you? We have to now use this context to realize what we're talking about. We can see meters and seconds are in the question for us. So in context, it means I will travel the so not me, the rocket will travel 5 meters per second. Meters per second. How do I know it's only 1 second? Skylar?
Because T doesn't have anything. Well, I guess the 5 is kind of part of it. But that's just like simplifying it down as far as you can go.
What would the number 5 look like as a fraction?
5 over 1.
It'd be 5 over 1. And then we're talking about rate of change, rise over run. The rise is my meters, and my run is my seconds, or my distance, and my time. Does that make sense to you?
Yeah.
Okay, so you can look at it that way. All right, and what's this contextual description of the initial value? Emma? What is the initial value? Okay, and what is it? 2. What's that mean? The distance it was already at when it started, when it took off. So when it launched, it was 2 meters in the air?
No, it's 2 meters tall.
Was it 2 meters away from where you
A 2.5 foot rocket's distance traveled in meters based on seconds, modeled by the following function. That 2 means something. First of all, does it mean seconds or does it mean meters? Well, what is the dependent variable? Distance. So this has to be a distance of 2. That 2 means 2 meters.
Maybe the stand it's sitting on?
Exactly. If a rocket's going to be shot off, you're going to put it off of a stand. And that stand's going to be 2 meters tall. Wow. See how we can figure that out? What's actually going on in the situation from the information given to us? That's what contextualizing means. So the initial value is the 2 meters above the ground that the rocket was launched from. Probably a platform, right? Questions on that first one? The more descriptive you can be in that contextualize, the better. All right, so let's look at number 2. The first one, we had an equation. And that was pretty easy to find the stuff. This one, we don't have an equation, but we do have a graph. So the cost of 6 people to travel in a taxi in New York City, based on the number of miles driven, is shown by the following graph. Let's start it off. What's our dependent variable? Cost. How do you know that? Right there it says based. Good. I don't know if you guys heard him, but Luke had a different reason why he chose C. How many people chose it because it said C based on? Good. Nothing wrong with that. There's more than one way to look at this problem, as is usually the case. What did you say, Luke?
Because it's the Y.
Because it's the Y value. And my Y value is always the output or dependent variable. So I can look right here and know right away that my dependent variable's got to be C, therefore my independent variable has to be my input or miles driven. Good. What's my rate of change?
1
How'd you get that?
You can look at the graph. Like you find 2 points where it's actually on, and then you, I don't really know how to explain it. You go down however many, and then over however many.
I basically got to find my slope, my rise over my run, right? There I got to find at least 2 lattice points, count my rise and my run. I ran 2, I rise 1 over 2. My rate of change is 1/2. What's my initial value? 2. How do you know that? Where it crosses the y-axis, right there. It's also where my input is 0, which is cool. And so the equation line is C equals 1/2 m plus 2. What does the rate of change mean in context? In this situation, what does the rate of change mean? Yes, sir.
For every one person that gets attracted, it costs it's 2 miles.
For every dollar, right? For every dollar, the taxi will travel 2 miles. Okay. Anybody want to say it differently? Could I say taxi will travel 2 miles for every dollar?
Yeah.
That's the same thing, right? It is the same thing. My rate of change is still 1/2, but does anybody see how that can be confusing? Because I said it backward, didn't I? Okay, so just realize that can happen. You just got to determine which thing's independent, which is dependent. Okay? I got one more way I could say it. How about 50 cents per mile? Could I have said it 50 cents per mile? That's $0.50, right? Good. What's the initial value? $2 for what? Just to ride in the taxi. Just to get him to say to go. You got to give him $2 plus 50 cents a mile, right? That's figuring out the context. What's going on in the situation? Questions? Let's do one more and we'll stop, okay? Because so far we've done it with an equation and we've done it with a graph. What if we just have a situation? We still have to find those 4 parts. Dependent, independent, rate of change, initial value. So we got Planet Wiener receives $2.25 for every hot dog. They spent $105 for 25 packages of hot dogs and 10 packages of buns. Think of a linear function that demonstrates profit based on the number of hot dogs sold. Nick?
Well, I don't have a function, but I know the dependent.
Go ahead. Good. P is based on H, so I know my independent and dependent. Austin? Rate of change is most definitely $2.25. That's how much I get per hot dog, right? I know it says for every, but that's just another way of saying per, right? Here, kitty, kitty, kitty. Right? The per helps us remember our rate of change. Initial value then is what?
105.
105. Maybe. What's happening here? Yeah.
It's based on profit, and they had to spend 105 to actually get the material.
So what is that 105?
Minus.
It's a minus 105, right? Because we had to spend it so we could have hot dogs to sell, right? So now what's the equation on the line? P,
Equals 2 point.
not plus 105, minus 105. Because we got to spend $105 to have hot dogs to sell, right? Herm dogs. All right, so in the context, what's the rate of change?
Every hot dog.
It's the $2.25 per hot dog. What's the initial value? The $105 spent for supplies. What's your homework? Even questions. When you're done doing them, check the answers in the video. Y'all have a great day. I'll be posting that video and a reminder on the Google Classroom. Y'all have a great day.
Like these even questions?
No, section 2.2, even questions. Only